All right, good morning, everyone. So, yeah, my talk, I'm going to talk about the new Named Tuples feature, which is just coming out in Scala 3.7. About me, I'm an engineer at Mybex Software, and I used to work at the Scala Center until last year. Recently, I've done work on upgrading Mill to Scala 3, the Mill build tool, and pipelining in the Scala 3 compiler. And that's my website. So, I want to talk about basically why are the named tuples being introduced to the language. What are they? How do they relate to structural types, structural typing, what is useful about doing things with structural typing, and yeah, how to use named tuples, and what are their limitations, because I basically spent like 3 months or so working on demos for this talk, so I believe I understand the limits pretty well. So why do we want named tuples? First thing, yes, there's code, a lot of code in this talk. Case class, if you ever had a case class with many, many fields and you want to pattern match on it, then maybe you have this situation where you have this huge line of wildcards in your pattern and you only extract one field. There is an alternative, which is the type case pattern, but with this named tuples feature, this all goes away because we can just reference only the field we want to use by its name with a little label. So it looks a bit like named arguments, except it's in a pattern. And I looked in the Scala 2 bug checker, and since 2012, people have opened an issue for this. So yeah, it's been a well-wanted feature. Next problem it sort of solves is this idea that when you want to have multiple return values, should you bundle them into a case class? Often that's a bit too much noise, so maybe you just use a tuple, and now you're left with this problem that we don't know which side is which if they're both the same type. Like the partition method on sequence takes a predicate, and then it splits the list into those that match, those that doesn't. And with the named tuples, we can now add labels to each side of the multiple returns, so we can tell exactly which is what. So, now I know it's the left that is the matches. Before you'd have to look at the documentation, but now it's sort of, if you hover on the type in the IDE, then it just tells you. Next, yeah, there's this idea that we already have structural typing in Scala since 2.6, so that's ancient times. But there's a few problems with them that named tuples addresses. So the really convenient part about structural typing right now is you declare some arbitrary type, like this record, and you add any number of fields as structural refinements. And then it doesn't matter how many refinements you have, as long as you have this name and this age, then you can treat it like a person and access these fields. But because there's no sort of predefined order of how these appear in the type, there's no way to programmatically, like deterministically say, I know which location in memory the name will be, so it ends up basically needing to be dynamic access. So here's how you define normal old structural types. You extend selectable trait, and you define a select dynamic method, which takes a string. This could be an inline method, so you can have an attempt at optimizing it, but you really have to use macros, because the only way to turn your dynamic thing into a safely structurally typed person is with a cast. And you can't really construct these types programmatically from data, only using macros. And yeah, when you select the name here, then it gets resolved to this select dynamic method and does a cast again. So yeah, named tuples will improve this, so you don't have to use macros. Here's a more at a distance example. Say you're writing a blog generator, and you need to extract the front matter from some markdown, which is typically like some YAML at the top of the file. And I declare some schema here as a structural type, refining this front matter thing. And I have heterogeneous data, so I have a string, I have a Boolean, I have a list of strings in there. And kind of the only way to conveniently define this is to store a hash map where we use the lowest common denominator, so everything's effectively list of string. And then when we select, we have to basically stick to some sort of convention. So we have to say, oh, if it starts with is, then it's a Boolean. If it ends with s, then it's a list. Otherwise, we have to sort of try and pick the first element. And you can make this, the only way to make this safe and not just dynamic is to pass in some sort of schema in the constructor, which is again very difficult to do without macros. So with the named tuples, this will become easier. But why would you even want these structural types? So the good thing is that, yeah, if you have your memory is too full and you don't want to think of any names to bind all these like hundreds of fields together, you don't need to think of a name, only the fields count. It's also really useful for these sort of temporary ad hoc types, such as if you have a chain of methods and you have some sort of temporary value in the middle, that temporary value can get a structural type, so you don't need to go and declare some class elsewhere. It can just exist in this temporary expression. It can be useful to provide a narrow view over data. So let's say you have some JSON endpoint with millions of fields. You can just narrow in on the fields you want to use in your API, which kind of makes it less coupled to changes because you can ignore the ones that disappear. And yeah, the most convenient thing with them is that if you have two structural values, then you can usually compose them and keep the fields of both while preserving type safety. And the fun thing is when you use basically type level computation to take a value, like a schema value, and then derive a type from that, which then can be used to validate further expressions at compile time. So here's an example Spark that would benefit from structural types. Using the dataset API is basically like a untyped version of SQL on top of the data. So we have these unsafe operations here, like the age column we can apparently compare to 30. But this is just read from some sort of dynamic file. So we don't really know if it's going to work until runtime. But let's say you could have a schema as a type, then you could have a structural type that would validate that, oh, when you select the age column, then the comparison operation is valid. And yeah, right now you'd have to use macros, but with named tuples, again, macros don't need to be used for this use case. And here's another example. We have Scala SQL, which is this library to help you do ORM, or just basically generate SQL from these sort of query statements here. And the idea is that you can have a type-safe selection of the population column or the name column from this city table. But the inconvenient thing is that you have to define your city with this strange type parameter here, t, which itself has a type parameter. So yeah, like the population column is this t of long. And the idea is that when you're inside this query, then it's a city of expression. So it would be population is an expression of long. But then when you actually run the query and return from the database, then it's this city of ID, which just returns the type itself. So then the population would actually be a value long and not expression of long. So this is kind of a bit ugly, and you have to specialize your data type to this thing. And with named tuples, this goes away, and you could just have city as an ordinary case class without this higher kind of data parameter. Yeah, and the reason we do this thing in the first place is that this database could be sort of agnostic, but this, so you write the code once and it runs on any kind of database. That's the idea of this. So finally, we can get to named tuples. So this went through the Scala improvement process number 58, and it will be stable in Scala 3.7, and you can try it now, unexperimental in RC1. And yeah, this is what they look like. So yeah, we say we have a type person with two fields, name and age. And it looks a bit like function parameters or just case class if you drop case class and the name from the front. Then we have value syntax. So I can construct a person by providing just a name and an age inside of parentheses, or any label that you want to give at all. You don't have to pre-declare this. You could just have this value on its own. And you do get type inference. So yeah, now I can select the name and age as you would expect. And they have pretty good type inference. So if you wanted to do a JavaScript style API, you could. I wouldn't recommend this because it will box this far, but whatever. You can declare these functions that will do something to mutate state, and you get an infer type with all those accessors. So that's pretty convenient. This is what it looks like when you do pattern matching. So you can deconstruct the person named tuple by its fields. So you provide field labels in the patterns here. And you can even swap the order. So I put age first instead of name. It doesn't matter which order it comes in. And you can even only drop some of the names, as I mentioned before. So the convenient thing is that this also comes to case class, so you can ignore some fields. How do they work? So yeah, here's the name tuple type. And is it more similar to a case class person, so a product type? Or is it similar to that record example with the structural typing I showed earlier? And the answer is that it's more like a product type, but it is not Scala product, but it is a product type, as in a algebraic type with defined fields. Here's why it is not a structural type. You cannot create an intersection type of two named tuples. So we have two types here, has name, has age. So you would think they have separate fields, but the reality is that these are both referring to the same field in the underlying class, which is tuple1, for example. So when you try and create an intersection type of these two, then you're basically saying the field _1 is called name, and it's also called age, and it also stores int, and it also stores string, which is not possible. So you get compile time error if you try and select those. But yeah, and this is what it desugars to. So the type person is actually this desugaring to name tuple, which is a type, which is basically a pair of two tuples, string tuple on the left, which is the labels, and the actual underlying type here. And these names are only available at compile time, so you can't access them at runtime, but there are ways around that. And yeah, this is the actual underlying type, so it really is just a tuple with some labels added at compile time. And this further desugars into generic tuple types. So on the left, we actually have like a compile time list of the name literal type, age literal string type, and empty tuple. And basically, because we have this first class types, that means that you can construct freely name tuple types any way you want without the use of macros. And this is what it actually is. It's this opaque type. So all name tuples derive from any name tuple. And then the name tuple is really just type alias to the T on the right. So it really is just zero cost wrapper of tuple type. Okay. So you also get a bunch of generic operations. So you can convert zero cost from name tuple to tuple, from tuple to name tuple. You can also use the type class derivation framework. So that's this mirror. And you can construct a name tuple type from any product type. And here I have the conversion of the person to a tuple, which is product. To get around that idea that you couldn't intersect them, we have concatenation. So again, we have something with a name, something with the age. And with the ++ concatenation operator, now we have access to both of those fields. And there's even a compile time check to make sure you don't try and concatenate age with age by proving that the names are disjoint. There's other convenient things. So we have this map operation. So this is like a match type. And what it could do is, let's say, box each of the value types in option. So if I want to construct an optional person where each field is an option, I can do that. So like it has a name but doesn't have an age. Then we have this really good one, named tuple from, which can convert a case class type to a named tuple type. And this is really powerful because it basically provides you a schema to construct a named tuple from. So here I'm constructing a named tuple with the same fields as city, but it's not the same type. But we'll see later how this is really convenient. And here's what you're supposed to do with it. So I showed you before the multiple return values. You can use it in testing to define like a list of like a big blob of data that you want to feed into your test without having to declare something ahead of time. This is something I've been using it for, which is generating invoices. So this is just a way to, at the script, you could have a script with a big blob of fields and whatever, simple data at the top, and then at the bottom of the script, then you convert that into actual proper data and use it somehow. But it's quite nice, I think. Yeah, and here's the final reason you use them, which is this, again, the improvements to the already existing structural types in Scala. So the new thing what's changed is you still extend the selectable type with some arbitrary class, but you have this fields type, and it has to be some sort of concrete named tuple type, and it's the same with select dynamic, but yeah. So here I have f, which is foo, and I refine the fields type with this concrete named tuple type. So when I access x, which doesn't exist, then it resolves to select dynamic. And the important thing here is that we actually have access to the fields within the class itself, so we can inspect it from the select dynamic method. Previously, you had no idea what the outside world projected onto you with the fields, so now you can actually like enforce safety within the class itself. And so I want to show a lot of demos that I've prepared on my GitHub Scalar 2025 repo, which is here. It's public. So there's actually a lot more than I'm going to show in this talk, so I encourage you to take a look. So the first thing is, obviously, we've got to convert named tuples to JSON, which is, in this example, basically dynamic typing, but whatever. So I'm using the Ollama API, which is open source LLM client, using STTP library and upickle library. I'm calling it here, and I'm going to construct a JSON object out of a named tuple type. So I could just pass any arbitrary named tuple, and I have a on-the-fly generation of deserialization and serialization. And then right here at the bottom, you get a JSON with many, many fields, but I only care about the message field, and within that, I only care about the content field. So I just construct on the fly a little named tuple type here and extract it and print it. Next thing is chimney. You could do a sort of mini chimney thing here. So I want to convert between user v1 and user v2. Well, within the conversion method, I can convert it to a named tuple type using the mirror framework. Then I can use concatenation to just add this age field, so a default value if you like. And then finally, as will convert it to the user from a named tuple to user v2, again, using the mirror framework. And yeah, this is a bit of a eager thing, so I could have made it more lazy, but it's very convenient to do this, and no macros needed. So next thing, I made a data frame demo. So let's say we want to analyze this text to count how many times each word appears. So it's the typical Spark example. So I have an external function here which converts the string to lowercase. Then I construct a column with this words column. So I didn't declare this ahead of time. It's just a type that appears magically when I give it this named tuple value. So I'm going to split the text by white space, whatever. Then I'm going to add an extra field. So again, lowercase column by calling this external function. And I'm accessing the words column with a structural field selection that I just generated from here. And then now I have the lowercase column, and I can group by that. And now I want to aggregate on the key, which is the lowercase column, and add this frequency column again. So I'm using named tuple concatenation here to invent this frequency column. And I'm going to sort by the column, yeah. So then I get this in the end, and this is all type safe and using these ad hoc types that come out of nowhere. Yep, then the next thing I promised to show you was that we could do Scala SQL without that funny type parameter here. So it's the same thing here. We just construct the expression in a different way using this, the thing I just showed you, the selectable with the fields method. So we can take the city case class, and then I define this expression thing, which is parameterized on the schema, which will eventually be the city. And then I have to refine the fields type. I would get this expression as the C within this city select filter. So when I'm selecting the name, then it's going to be this expression type. And precisely, I use the named tuple map to map each field into expression. So the name is now this expression string, the population is this expression of int. And then when I select name and population, then it's resolving to select dynamic, but we box it in the expression type. Whew. Quick. Endpoints. So now I've got another demo, full stack application. So going full speed. We have a CRUD application, notes. We're going to create notes, delete notes, add notes. So I'm using this mirror ops mirror thing that I showed last year at Scalar to basically generate this object, which is a named tuple selectable type, which contains a bunch of endpoints. So each of these things get turned into a field and the named tuple, which is an endpoint. And then I construct a client. This is in the browser, so I'm using the fetch API. And so each of these is going to return a future, but this is what it looks like. So I'm going to create note send, returns future, whatever. Now on the back end, I use the exact same schema object here. And now I can create a router for my server here. And the server has a routes type, which is a named tuple type derived again from all this stuff, from the schema, from this. So I have to provide the server logic for each of these things. And it's parameterized on this database. And the database I passed in the main method, so it's going to be this log-based store. And what does this do? It's a database wrapping around that Scala SQL thing I just showed. And so when I run these things, I can insert values, select all the nodes, delete a node where the ID matches. This is all using the named tuple selectable stuff. And here's what it looks like. Wow, that's crazy. So this is Ghost T, and I'm going to zoom in here. So what's going on here is running the main method is loading the database from the store, loading the routes. And then I go here, and I have my little server application that's great anyway. So I make a note, create a note, refresh the page. Oh, it's still there. Kill the server, and it's gone. Then I'm going to run it again. Loads from the database. This new one. So it's still there, and I can copy some song lyrics from 365 Charlie XCX, put it in the thingy, can analyze using data frame, get the frequency of the words, whatever. So bumping is the most popular word in the song. And here's what it looks like. Have a web page, it's written in laminar, have the client here, and I delete the nodes, I send it from a named tuple type here, turns into JSON, returns a future, which I convert into laminar streams. Here's the data frame stuff. Every type is nicely inferred. I get the frequency column exists here. Don't look at that one. It's ready at the end. Anyway, yeah. So like you should see that in metals, I get nice type inference. Anyway, and then on the front end, back end, sorry. So I have the routes. And I actually have this static thing as well, so I need to serve the index and the JavaScript. I concatenate these two endpoints to get a schema. I create a router from the schema. It has a routes type, which is a named tuple type. I pass that in. I construct the thing with the log-based store, which is a database that converts all these expressions into real operations. Yeah. Okay, so how do you do all this stuff? How do you construct these fields? There's several ways to manipulate types. We have match types, which is like pattern matching on types. We have the mirror framework, which is like a compile time reflection of the fields and labels, the structure of a type. We have the compile time ops package, which lets you like convert literal types into real values, so you can convert these labels into real strings that you can use at runtime. We have the inline match, which is like pattern matching, but it resolves at compile time, and that can be used to compute types. And then, of course, we finally have macros, which if you stay in the next talk, you'll learn all about. I encourage you to look at those demos. Now, what I said, I'd discuss some limitations of the named tuples, so we should do that. First thing, there's no recursion when you construct them with a literal. So, yeah, they're not the same as object literal, which you can do in the current way with this. If you just extend selectable with an anonymous class, then you actually infer the fields dynamically. So you will have a refined type with the X field and the Y field, and I can even have recursion here to refer to the field in the same scope. But if you try and do it here in the named tuple, then it's looking from the outside scope, so it doesn't know that it's the same X here. So this is kind of a problem if you want to have recursive types like some sort of config object that can define your entire website and you self-refer to other fields. So this is what I wanted to do, but it's really hard to do that. One way maybe to get around this could be if we could have explicit types, then you could do the thing where you could self-refer to a field because you know its type. And then we would need some way to, I guess, have a self arrow here, so you could point to a field and this, something like that. And the other thing is, because it's an opaque type, this means that it's really hard to do match types with them, because there's no way to say, is this type name type, or is it a name tuple type, or is it some other type? You cannot do that in the cases in a match type. So I open this issue, but basically it's like a design decision. So because it's opaque type, there's no way to get around this. We should have designed them in a different way. But you can get around that if you basically have like a schema that's fully named tuples, and then somewhere inside that you can expect a label and say, oh, this label is like my escape hatch or my splice or something, and then you can put a sort of a branch in that way. Here's how you do that computation with the named tuple types. So, yeah, you can. There's a bunch of built-in ones. I showed you the map. Concat is what you get with the concatenation operator, so it just takes the left and right and puts the fields together. The from converts from case class C into named tuple type. Then you can access the names, so the literal types of the labels, you can use as names. Drop names is the other side, so you get the values. And if you have no idea what a match type is, it looks like this. So if you wanted to, say, define a match type that selects the type of the name, so some string, age would be some int, then it looks like this. So you pattern match on the T, you see it's a named tuple, you get the left and right, you then match on the left and right, and you can deconstruct it as this generic tuple type and do the typical recursion here. So here's the recursive step. And then, yeah, basically I find some or I don't find it. I would go to questions there, but I have 1 minute. So again, please look at my, I have a lot of demos here, so here's one of the things I think I wanted to show, which is that, yeah, if you put in your named tuple type some sort of escape hatch here, then in your sort of pattern matching, you can look for this special thing and do branching logic. And yeah, you can see the full stack application I just demoed. And then something good, if I did have time, would be this a llama demo. But I don't have time for that. But yeah, experiment with that. Hopefully, if someone collaborates with me, we can make a proper library. I don't know. Yeah. So I'm done.